Okay, so good morning, bon dia. So yesterday we spoke about certain aspects of Milnor's vibration theorem, and also in David Massey's lecture we saw many interesting things about that same topic from different point of view. I will start by recalling and saying in different words the same things we said yesterday, and all of that I will do with the screen, because I think it will be clearer. We can see pictures and so on. And then I will remove the screen and we will continue on the board. Okay, so remember, for this first part, let me restrict to the case of one holomorphic function. So we take one function in n plus 1 complex variables, taking the origin into the origin, with a critical point at the origin. We consider its vanishing set and the link, which, we say that we have the local conical structure that gives rise to this. In other words, given any complex, real or complex, so given any real or complex analytic set and a point in it, we know that there's, for every sufficiently small sphere centered at the point we are looking at, meets transversally the regular points of the set, and it meets, if we consider an appropriate, if we consider a Whitney stratification, then we have that every sphere meets transversally each Whitney stratum. That gives us the local conical structure of analytic sets. In other words, when we have an analytic set, we take the intersection with the sphere, that gives the link, and what is inside the ball is the cone over the link. And in fact, we have a homomorphisms of pairs taking the cone over the sphere to the ball, and the link, the cone over the link, is the variety. And this gives an idea of the proof. The proof consists in constructing a flow such that all integral curves converge to the origin. They are, whenever one integral curve touches the analytic space, it is contained, all of it is contained in the space, and that gives us a way to make this contraction, to have this conical structure inside. In other words, to reconstruct this thing inside, we look at the intersection with the sphere that gives this variety in general, a manifold when this has isolated singularity, and then we just make that picture smaller and smaller and smaller until it degenerates to a point. All analytic sets are like that. This shows somehow the trifold knot. Of course, this picture is in R3, so we have troubles, but and that represents the link of the complex singularity. Here should be a 3, not a 5. C1 square equals C2 to the cube. That gives the trifold knot, and then making that trifold knot smaller and smaller and smaller and smaller, we reconstruct this algebraic curve. Okay? And David yesterday told us how to prove that when you have C1 square equals C2 to the cube, how to construct the link of it by giving an explicit parametrization. In fact, the same technique, absolutely, just the way he told us how to do it, works in general. Well, we'll see it now. So if you have a non-isolated singularity, we have the same phenomenon. We have a local conical structure. For example, if you take a point here, the link will be just a circle, and the cone over the circle is the disk. Nothing very interesting. Now, if you are, for example, in a point here, in this intersection, now, if you take the intersection with a smaller sphere, that is a little harder to visualize, but it's not hard. If we take the intersection with the red plane, that gives a circle in the 2 sphere, and the intersection with the green plane gives another circle, and then the link of a point in this axis here will be the union of 2 circles meeting at 2 points, 2 antipodal points. What if we take the link of the origin? That will be the intersection of these 3 planes with a smaller sphere centered out here. Well, it's very easy to see that it will be the union of 3 circles. Each plane gives rise to a circle. Okay? Now, more interesting somehow is the case of this kind of plane curves, where these two are relative prime, this condition guarantees, it's not obvious, but this condition guarantees that this function is irreducible. It has only one irreducible component. And one can parameterize it just as David did yesterday for the 2-3. And then it's an exercise to show that the link is always a torus knot of type PQ. What does it mean, torus knot? Well, what's a knot? A classical knot is a copy of the circle embedded in S3. Okay? Now, in S3, you have many tori. Take the standard torus, for example. And now, suppose you have a knot that you can wrap around that torus in some way or another. Okay? That's a torus knot. And when you're wrapping it, it will go around a number of times in this direction and another number of times in the other direction. If it goes P times and Q times, it's a torus knot of type PQ. Okay? And so it's an exercise to show that for these curves, the corresponding link is a torus knot of type PQ, actually QP. So for example, this corresponds to the singularity C1 to the 4 plus C2 to the 3. And if you see this is a torus knot, if you start here, it goes up, down, up, down, up, down, up, down, and it closes. And if you count, it goes 3 times around one direction, 4 times in the other one. Now, if you consider more general algebraic curves, here we were considering a very simple type. In general, they are not so simple. So if you consider any plane curve, how is the link? It's very beautiful theory. We won't go at all into details, just to mention because it's very, very beautiful. And as David told us yesterday, every plane curve, say suppose it's reducible with one branch, can be parametrized, and it has what is called a Puiseux parametrization. Now, the Puiseux parametrization gives us pairs, a finite numbers of pairs that describe the topology. The first Puiseux pair describes a torus knot of this type. For example, in this case, these have only one Puiseux pair. So the link is a torus knot of type PQ. Now, suppose you have 2 Puiseux pairs in your parametrization. How you construct the link? Well, you start with a torus knot, or you start with a torus, and then the first Puiseux pair tells you how to construct a torus knot there. That's the first step. Now, second step, you take your torus, your knot. The knot is a circle. If you make the circle fat, if you multiply by a small disk, you have a flat circle, and then what you get is a torus, a knotted torus. And now, on that knotted torus, now you can wrap another circle in some way, going P times in one direction, Q times in a different direction for some PQ. Okay? That's an iterated torus knot. Now again, if you have 3 Puiseux pairs, now you take the new pair, the new knot, you make it fat, you get a torus, and on that torus, you wrap a torus according to the third Puiseux pair, and so on. Okay? So that's a way for constructing all links of plane curves. Very beautiful. So for example, this corresponds, I don't have the polynomials here, but those blue-green are, if you think, if you make this torus, the red one, fatter, you will see that these curves are being knotted around that torus. That corresponds to the link of a plane curve with 2 Puiseux pairs. Now, what about higher dimensions? Many beautiful things to say. It's fantastic. That's a theory that has been studied, well, starting with, I would say, Felix Klein in the 19th century, and then many great mathematicians. In the 60s, became a fashion. It was a very important topic to construct exotic spheres and manifolds in general. I mean, we have the definition of a manifold is a trivial definition. But now, how do you construct interesting manifolds on which you can put your hands on? It's not so easy. Complex singularity gives you a fantastic tool for doing that. Whenever you have a complex polynomial from Cn plus 1 into C, The zero set is a complex variety with an isolated critical point, singular point. So away from the origin, you have a complex manifold of real dimension 2n, and when you intersect with a sphere, you get a 2n minus 1 real manifold with a very rich structure. And the fact that it is algebraically defined allows you to do many things. The fact that you have mean of vibration allows you to study the topology and so on. So it has been a very rich source for producing interesting manifolds and interesting objects for topology and geometry in general. So in particular, for example, if we take this particular example, in 3 complex variables, this was studied by Felix Klein in the 19th century. And then he showed, with different words, he was not speaking about the link and so on. But at the end, what he does proves, has as an immediate consequence that if you take this, then the link, which is the intersection of the vanishing set of this with the unity sphere in this case, is just taking the 3 sphere. Think of that as being the points in C2, complex space of dimension 2 of unit length. Think of the 3 sphere as being that. And now, on C2, you can consider the matrices, all matrices of the form e to the 2 pi I over r, 0, 0, e to the minus 2 pi I over r. Obviously, that's a cyclic group of order r, acting linearly on C2. It acts by isometries on C2, so it acts on the 3 sphere. You can take the quotient of the 3 sphere divided by the action. It's a 3 manifold. Which manifold? That's exactly the link of this singularity. And like that, you have many, 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 many beautiful examples of, in dimension 3 and in higher dimensions. In particular, in dimension 3, it's known that all the links of singularities are of a special class of manifolds, which are called Wallhausen manifolds, which is a very important class of 3 manifolds. And these are all Wallhausen manifolds with something which is, each Wallhausen manifold has an associated intersection form. I will not come into details. But the manifolds coming from singularities are all Wallhausen manifolds with negative definite intersection form. And then a natural question is, amongst all the Wallhausen manifolds with negative definite intersection form, which ones appear as links of surfaces in C3? Open question, we don't know the answer. We have many examples, we have necessary conditions, but we don't have sufficient, there is not a characterization. It will be very interesting. And there are many Wallhausen manifolds with negative intersection form that do not appear as links of singularities. For instance, take any 2-dimensional oriented plane bundle over S2, and take the unit circle bundle. So in each 2 plane, you take a circle. So what you get is a 3 manifold. You get for each point in the sphere, you have a circle. You have a 3 manifold. And if your bundle has negative Euler characteristic, then the intersection, this is a Wallhausen manifold, and if the Euler class is negative, you have negative definite intersection form. Yet, these very simple manifolds, the circle bundles over the sphere, they cannot be realized as links of singularities in C3. Okay, so this is just an example. So this is a very interesting question. In higher dimension, there's a lot more to say, but I will move to something else. Now, going back, so let us recall that given our function in n+1 variables, holomorphic, with a critical point at the origin, we have the vanishing set, the link, and then the fibration theorem, classical fibration theorem, says that this is a locally trivial fibration. Okay? So there are no critical points. The fiber over each point is a smooth manifolds. All the fibers are diffeomorphic. And each fiber has a product neighborhood. That's what locally trivial means. Okay? And we saw also that there's another way. So before, in his book, Milnor studies this fibration, basically, and he proves directly that this is a locally trivial fibration. He proves that this map has no critical points, it's a surjection, and he proves that you have a locally trivial structure directly on this sphere. However, it's easier to understand that theorem going to an associated fibration, a different way of looking at that fibration, which is given epsilon sufficiently small so that you have a Milnor sphere, you choose delta very small with respect to epsilon, and we take a Milnor tube, as we did yesterday. I'll come back to this. So a Milnor tube looks something like that. So you have the map F, you take a 0 here that corresponds to the special fiber, and you take a sufficiently small circle here so that the fiber over each point is transversal to the sphere you have fixed. Okay, so we consider the Milnor tube. Here I'm considering a closed ball. This is a closed ball. And then I'm assuming that each fiber here is transversal to the boundary of this ball. Then you have a locally trivial fibration. And this is usually most people, in the literature, this is also called the Milnor fibration theorem. Myself and other people prefer to call it Milnor-left fibration. Why? Because Milnor didn't really prove that this was a fibration in his book. He proved it in a previous article for isolated critical points. And then in his book, he proves that the fiber of this map is diffeomorphic to one of the fibers of this map. But he did not prove that this was a fibration, because for that he was needing some ingredients that were not known at the time. And after a time, Ledun-Trang proved a much more general result for functions defined not in Cn. But here you can replace Cn by any complex analytic space, as complicated and as singular as you want, and you have a version of Milnor's fibration theorem essentially in this language, in this setting, in a tube. That's what Ledun-Trang proved. In particular, it applies to the case when the function is defined on Cn. Okay? And the idea for proving this technically is not so easy, it's not difficult, but the idea is very clear. You have the tube, and you know that the map F restricted to the tube has no critical points, because the critical value is inside, at the origin. So this is a submersion. Now take here a vector field, a never vanishing tangent vector field to the circle. Since this is a submersion, you can lift that vector field, the vector field tangent to this tube, and transversal to each fiber. So at each point, say the vector field is pointing that way, so when you come here and you have the fiber, the vector field is transversal to the given fiber. And since the fibers are transversal to this sphere, you can adapt the vector field at the boundary so that on the sphere, for points on the sphere, it becomes tangent to the sphere. And so you have a vector field defined on all the tube, transversal to all the fibers. It's integrable. You can do it. You can lift it to a smooth vector field, in particular integral, and tangent to the sphere. And then that using that vector field, if you have any fiber, you can move it slightly to take it to all nearby fibers, and you prove that you have the locally trivial structure. So that's the idea of the proof. Now, once you have the theory, once you have the fibration on the tube, how you get it on the sphere, that's something we mentioned yesterday. You construct a vector field which is transversal to all spheres centered at the singular point, and is transversal to all the tubes. And now, given a point in the tube, you take the integral curve of that vector field, and you travel along it until you arrive to the sphere. And you get a map from the tube to the sphere. That gives you a homeomorphism from the Milnor tube to the complement of these caps. And so going backwards, now given a point here, you take the unique integral line of that vector field passing through this point, you travel backwards until you meet the tube. That gives a map from the sphere minus the caps into the tube. And now you project by F, and you get a locally trivial vibration on the sphere minus these caps. And then with a little bit more work, you extend that vibration to everything except the link. Okay, so that's the idea of the proof. Now, as I said, Milo proved it directly on the sphere. All of this is just saying what I said before, and just here a reference if you want to see details of how the equivalence of the two vibrations go in the general setting for maps on any arbitrary complex analytic spaces. We did that in detail in an article with Cisneros Molina, Jaguades Nossi, and myself in Advances in Mathematics 2009. Yeah, all details are there. Now, what about real analytic map germs? So the starting points are theorem by Milnor himself. He proved it actually before his book, in a previous article that I mentioned ago, was never published. The article is from '66. And you have the zero set, you have the link. We assume very strict, very restrictive condition that zero here is an isolated critical point. When you consider maps, holomorphic maps from Cn+1 into C, the origin is an isolated critical value a fortiori. Just by being holomorphic, the critical values must be isolated. So this is an isolated critical value for holomorphic maps into C. Here, in general, the critical value will not be isolated. In general. And now, moreover, in the holomorphic case, you are not asking for isolated critical point. Having isolated critical value, which you always have, is enough. So here is a very, very stringent condition, very strong restriction. But now, with this restriction, Milnor was able to prove quite easily, it's an exercise, exactly the same proof I gave before, that if you have you consider the tube, then you have a locally trivial vibration on the tube. And also, you can inflate the tube as before and get a vibration on the sphere. Okay? Now, the big difference that I didn't mention here in the holomorphic case is that when you consider this vector field that takes the tube to the sphere, you are, let's say, inflating the tube with that vector field. But if you have just stated like that, you have no control of what's happening when you go to the sphere. You know that there's a homeomorphism, diffeomorphism from the sphere into the tube. But which diffeomorphism it is, I don't know. So when you want to write down the function that goes from the sphere into here, and then you project, you don't know what function it is. You know it is the projection of a locally trivial vibration. But which function it is, you don't know. In the holomorphic case, there's an additional thing you can do, is that you can construct this vector field in such a way that along each integral path, the value of f at points in that path has always the same argument. The complex number f of set divided by its norm is constant along each path of this vector field. So when you come here, when you take that point here back to here, and you project by f and you divide by the norm, it doesn't change. So you know that the projection from here into S1 is f of set divided by the norm of f of set. In the real case, you cannot always do that. So you always get a vibration, locally trivial vibration on the sphere minus the link. In this case, over the n-1 dimensional sphere, because you're taking values here. But you don't know what is the projection. You don't know if this can be taken to be f over the norm of f. Okay? So this is a very nice theorem for a start, but as Milnor himself pointed out in his book later, this is not there are several weaknesses, and two of the weaknesses Milner mentions. One is precisely what I said just now, that the projection map may not always be chosen as this one. So you don't know in general what function this is. And if you don't know what function that is, it's very hard to work with it. You know it exists. Very good. And also, the condition of having an isolated critical point is a very, very, very strong restriction. So you would like to do something more general. For example, asking for isolated critical value is already much more general. Instead of isolated critical point implies isolated critical value. But this is more general, much more general. For example, the function x, y, z goes to x times y times z, has isolated critical value, but all the axes are critical points. So there are many. And still, even isolated critical value is a strong restriction. But let's see some examples. This is what we call now the twisted Fan-Briscoe polynomials. These were studied first by Sidinha, myself, and Verkhovsky in a paper we published. And these are these maps. So if you remove these things with the bars, you get the usual Fan-Briscoe singularities, which are complex, very nice, beautiful singularities. Now, when you put these are no longer holomorphic functions. They have a holomorphic part and an anti-holomorphic part. Now, it's an exercise, not easy, but straightforward to show that each such map, when you have these conditions, has an isolated critical point. And in fact, these singularities admit what we learned in Mutsuoka's lecture and Kosoris's lecture, a polar action, an action of S1 times R plus. And using that action, using the polar action, here we were able to show that all these singularities have a associated Milnor fibration with projection map F over the norm of F. And in particular, here sigma is any permutation of the set 1 to n. When that permutation is the identity, so you have singularities of type C1 to the A1, C1 bar plus Cn to the An, Cn bar. When you have those, then it's easy to show that those are the Milnor fibration you get is topologically conjugate to one of these fibrations. So that's why the name twisted Fan-Briscoe. When the twisting is trivial, you have a Fan-Briscoe singularity. Later, Oka showed that this equivalence was more. We only proved topological equivalence. He proved smooth differential equivalence of the corresponding Milnor fibrations. And these singularities are very interesting because they are, as I said, they are somehow the paradigm of mixed singularities and also polar singularities with a polar action. Now, another example, these were studied by Anne Pichon and myself. You take this, so you have a usual Fan-Briscoe singularity, but now you multiply by all of this. We've proved that you had a Milnor fibration in a tube. But then later, Cisneros Molina showed that these singularities actually are polar weighted, and therefore, from that, he deduced that you had a Milnor fibration on the sphere with projection map this one. And these have isolated critical value if you have these conditions on the exponents. So almost for all exponents. Another example, take arbitrary complex numbers lambda 1 to lambda n, non-zero complex numbers, and assume they are generic in some sense, and the convex hull contains the origin in their interior. Okay? It's an example studied by Santiago López de Medrano. It's published in a paper in Hironaka's volume of the JACA conference in 2009. It's very interesting. These functions arise from holomorphic dynamics. The zero set of this function is what is called the space of Siegel leaves of the holomorphic linear flow with eigenvalues lambda 1 to lambda n. So you have this very nice function. Now, it's an exercise to show that the critical points are all the axes. And so when you project the axes, they give rise to n lines passing through the origin. So for each eigenvalue lambda 1, you have lambda 1 multiplied by all norms. Let's say, so you have a line passing through lambda 1 in C. So you have n lines of critical values. So you have not at all an isolated critical value. And then what Lopez de Medrano shows is that on each of those lines split the plane, the complex line, into sectors. And on each sector, you have something like a Milnor fibration with fixed topology of the fibers, but the topology changes from one sector to another sector. And he describes how the topology changes from sectors to sectors. So that's very interesting, and well, somehow it points a line to work in the future, because if you consider real analytic maps into R2, the generic picture will be to have curves of critical values converging to a given point. So those curves of critical values will split the plane into sectors, and no hope to have a Milnor fibration with same topology over each sector. But on each sector you will have something, and that's the general phenomenon. So that's a line I think we should explore in the future along this line of research. Now, well, how to understand what is happening? When do you have vibrations? When do you have vibration on tube? When you have a vibration on the sphere, and so on? That's what I will discuss briefly now. This is work. So, well, when do we have a Milnor left vibration? That means a vibration in a tube. That's whenever you have a. Well, so these are topics that a number of people have been studying, Ruas, myself, and Berkowski long ago. The first one to study, I mean, when you have a vibration on the tube, when can you get a vibration on the sphere with projection map, the canonical one? The first one to study that was Alain Jacquemart, a student of Perron in 1889. Then he changed topic. Somehow the subject remained dormant for many years, and then, well, in later years, somehow this paper brought new light into the topic, and there are a number of articles by many people, and so on. So now let's talk about this with more care now, but we'll do it in the Blackboard. I don't know if there are questions so far, if you want to make questions.
So if that vibration exists, does this imply that the tube vibration exists or not?
Very good question. Let me come to this now. I'll answer it in a moment. It's a very good question. Yeah. Okay. So the answer is I don't know. Yeah, but I'll come to this in a moment. Okay? So you can see a map now from Rm into Rn. With an, let me assume with isolated critical value at 0 in Rn. Okay? And I'm assuming m bigger than n. So we take the vanishing set. We have the link, intersection of V with some sufficiently small sphere. Okay, and so the question is, when do we have a Milnor Le vibration on a tube. Okay, in other words, we have the vanishing set, this is V. We have a Milnor sphere. We take a, so we want to know when is there a Milnor tube, n of epsilon delta, so that F takes this tube into the small circle of radius delta. We want to know if this is a locally trivial vibration. So that is the first condition. That is the first question we want to explore. A very easy answer comes one. If 0 in the source is an isolated critical point, this always happens. Yeah, and just essentially by implicit function theorem. Why? Because in that case, every point in this intersection is a regular point of f, and since it is a regular point of f, the implicit function theorem tells us that in a neighborhood of it, the function essentially is like a projection. And since this fiber is transversal to the sphere, because it's a Milnor sphere, then all nearby fibers are transversal to the sphere. You have to do more carefully things. That's at a point, but now the link is compact, so you can do that with no problem. So when you have an isolated critical point, you always have a Milnor left vibration on a tube. Now, if you relax now the condition and you want to consider isolated critical value, then you have more troubles. If 0 in Rm in the target is isolated critical value, and F has the Thom AF property, and then one has such a vibration. Okay? So for example, in Mutsuoka's lecture last week, we learned that whenever you have a mixed polynomial mixed function into R2, the critical value is always isolated, and if it is strongly non-degenerate, then you always have this vibration. Yes, David?
So in those two cases, are those Milnor vibrations inside the tube equivalent to F over the norm of F on the sphere?
Let me come to that in a moment. No, in general, no. In general, the answer is no. For him, the answer was, I don't know. In this case, I do know. In this case, I do know, and it's no. Okay? I mean, I'll come now to this. That's exactly where I'm going to. Okay, so you have this. Now, Is this condition necessary? It's a sufficient condition. Is it necessary? The answer is no. What we actually want, the necessary condition, is that for every sufficiently small Milnor sphere, there exists delta sufficiently small with respect to epsilon, such that all the fibers over points in the circle of radius delta meet, well, sorry, I'm saying circle, well, on the sphere of radius delta, meet the boundary transversally. That is the condition we need to have the Milnor fibration. Okay? So, let me write it. The condition we need is for every Milnor sphere S epsilon exists delta, which is a function of epsilon, such that each fiber f minus 1 of t with norm of t equal delta meets transversally the boundary sphere, the boundary of the ball. Okay, so that's the condition we need to have a vibration on the tube. Sorry? Yes. Thank you. Thank you. Okay, so whenever we have a Milnor sphere, there's a sufficiently small sphere in Sn minus 1 in Rn, a sufficiently small sphere, so that for each point here, the corresponding fiber meets the boundary sphere transversally. That's the condition to have a vibration on the tube. And this condition is weaker than this condition. We have explicit examples of functions that do not have the term AF property, but do have a Milnor vibration in this sense. Now, once you have this, you want to see what happens on the sphere. And it's an exercise to show, and that's done carefully in my article with Cisneros, Molinas, and Snousy, and more generally, it's easy to show that whenever you have a vibration on the tube, so you have the tube. You can always construct a vector field. So there exists vector field such that one is integrable. Integral vector field on a ball minus the special fiber, such that the vector field is integral, it is transversal to all spheres around the critical point and transversal to all Milnor tubes. Okay, so using that vector field, again, we can inflate the tube to the sphere, and we get a vibration on the sphere. How do you do it? Given a point in the sphere, you go back to the tube and you project, and you have a vibration on the sphere. But in general, the projection will not be f over the norm of f. From the tube to the sphere, it is f over the norm of f. But from the sphere to the tube, you don't know what it is. It is traveling along the paths of some vector field. So you have no control of what's happening. So how to get more control of that? Let me go back to some ideas. The canonical pencil. This was introduced by Ruas, myself, and Verhovsky. We did it for maps into R2, but the method is exactly the same. So suppose we have a map F from Rm in the origin into Rn. Now, let L be a line in Rn passing through the origin. Okay? So we have Rm being mapped to Rn, and here we consider a line through the origin. Okay? Given that line gives a unique orthogonal hyperplane. Well, let's see. No. Well, okay, you have this line. There are several ways to do this. Now define x theta to be the set of all points in Rm such that f of x is an element of that line. So sorry, x sub L. Okay, so for each line, we can form this set. Okay? It is easy to see that if this is an analytic map, this is an analytic set. Why? This is just nothing but the zero set of taking F composed with the projection into the orthogonal plane. Okay? So the zero set of that composition is exactly this. And that's an analytic map. So this is an analytic space. It's an exercise to show, one, the union of all XL is the whole thing. It's all Rm. Two, the intersection of the XL is the vanishing set of F. And three, each XL minus V is smooth. Okay? So you have these XLs, well, they are parametrized by the lines in Rn, so they are parametrized by Ls are parameterized by R, P, N minus 1. And you have this like a pencil. So in particular, if N is 2, these lines are parameterized by a projective line, a circle. So what you have is the singular variety, and then you have all this family of real hyperplanes spiraling around this axis. So it's like a pencil. And you have it for any map. So in fact, you can define the same for every even continuous map. But now, what properties you get is harder. But for every real analytic map, you have this canonical pencil. Now, each of these each XL is real analytic at the origin. So it has Milnor spheres. In other words, for each XL, there's an epsilon such that every sphere of radius less or equal to epsilon intersects XL transversally. Okay? Definition. F is the regular if there exists a uniform Milnor radius for all XL. In other words, if there exists an epsilon sufficiently small so that each sphere of radius less or equal to epsilon intersects transversally each XL. Okay, so that's a definition. Sorry? Yes, for example, if you take maps from Cn plus 1 into C, every holomorphic map satisfies this condition. See? It's not obvious, but it is. It happens. I'll give now a characterization that will help. Okay? So for example, if we take maps from Cm plus 1 into C, so then each line is determined by an angle theta, say between 0 and 2 pi, and XL consists of all points in Cm plus 1 such that the argument of the complex number is equal to θ. Okay? Now, theorem. This is by Cisneros. Just let me say that the same concept in different words, in a different way, equivalent but different way, was also defined by Raimundo Antibar. Okay. Now, the theorem by Cisneros, Molina, myself, and Snousy. F is the regular if and only if there exists an integral vector field V on a Milnor ball minus V such that it is transversal to all spheres around 0 and transversal to all Milnor tubes so as I said, this condition, a vector field satisfying these conditions is always, you can always construct it without being regular, anything. The second condition is where this comes. And to each integral curve of V is tangent, well, is fully contained in some element of the pencil. So each element of the pencil is foliated by the integral curves of this vector field. Okay. So some examples of D regular. I'm afraid all my examples are good for maps into R2. I don't think we have do we have some more? We'll see. One. Every holomorphic map F from Cn plus 1 is deregular to all this twisted Van Briskon singularities. José Luis, all polar weighted, no? And all polar weighted singularities. Well, sums of the regular functions in independent variables. So, for example, you can take a complex polynomial and then in variables C1 up to Zn, and then some mixed polynomial in variables W1 to Wm. That's going to be, so you have a large factory of this regular. Yes. Yes. Yeah. So
Can you draw a picture?
yeah. Unfortunately, I don't have a good picture. I try to use my hands. Okay. So we have the Milnor tube. We know we can always inflate it with a vector field such that the solutions are transversal to Milnor tubes and to all spheres. Then that allows you to take the Milnor tube into the sphere. Beautiful. But now, we want to inflate the tube in such a way that when you're in the sphere and you go back, you have control of what is the map from the sphere into the tube. That's what we want. So that when you project, you know that the projection is f of z over the norm of f of z. That's what we want. Okay?
So what is this vector? It should be, what's its link with xi?
Let us just restrict this easier to get the picture to the holomorphic case. Okay? In that case, and thanks for asking. Now, in the holomorphic case, so each, let me say, each x, let me call it x theta in that case because lines are determined by the angle, and I want to emphasize the angle in that case. X theta is the union of all sets in Cm plus 1 such that f of z over the norm of f of z equals e to the I theta. Okay? So each of these varieties is a set of points here. Well, say x theta minus the origin. You remove the origin to avoid simple things. Away from the origin, this is the union of all complex numbers whose argument is this number. Okay? Now suppose that on the ball you can construct a vector field which is transversal to all the tubes, transversal to all the spheres, and the integral curves, each integral curve is fully contained in one of these guys. Okay? Then when you are on the sphere, you go back to the tube, you know that the angle doesn't change, the argument doesn't change. Then when you project, you know that you are going exactly here. You have perfect control of what is happening. Okay, so that is the important thing about this. Yeah? So it's clear now? I don't know if somebody has more questions. Well, we will come. And this is exactly what happens in higher dimensions. So with that condition, we know we have control of what is happening. So that's why this is the important condition for this regularity. This is the important one. So now suppose f has a Milnor left vibration on a tube. So we have the singular variety, you have the tube, we have the sphere, the Milnor sphere, and we know that the tube fibers over the circle or over the n minus 1 sphere here. Okay? So suppose you have that condition. Now, suppose further that f is the regular. Okay? Then the theorem implies that we have a locally trivial vibration 5 equals f over the norm of f from a small sphere minus the link, this is sphere of dimension m minus 1, into S delta of dimension n minus 1. Okay? So in other words, when you have these conditions, you have the following very beautiful picture. You look at a ball, at a solid ball in Rm. In that ball you have the singular variety, which is an axe. Around that axe you have the elements of the canonical pencil, which spin around that axe and fill out the whole space. Away from the axe, each element of the pencil is smooth, submanifold, nice. All of these guys meet the boundary sphere transversally. And the pencil itself actually gives you a locally trivial vibration over the sphere with fiber the XL minus V. Okay, so in fact, let me, that's important to state. So we actually get a vibration from the ball, the whole ball minus V into Sn minus 1 with projection map F over the norm of F with those conditions. And each fiber is XL minus V. And each, let me call it F, capital FL. Now each FL meets transversally the boundary sphere S epsilon equals the boundary of that ball and defines Milnor vibration phi equals F over the norm of F from the sphere minus the link into Sn minus 1. And the restriction of this to the tube n epsilon delta gives the Milnor left vibration on the tube. Okay? So we have two classical vibrations, one on the tube, one on the sphere. What we are doing is giving a vibration of the whole ambient space, the whole ball, that restricted to the sphere gives one, and restricted to the tube gives the other. Okay? Yes. Yes. Yeah. Sorry, you're right. Because this XL have two components. These are the points which, by f of z, fall on the line L. Now, when you remove the origin, you have one half line and another half line. So this has two connected components. Each connected component gives rise to one of the fibers here. Yeah, Raimundo.
How can you relate the fibers with each other?
Which fibers?
The fiber of each fibration. The fiber of the fibration, the ball minus B, the sphere minus K, and the tube fibration. Is it possible to relate the fibers, the topology of the fiber? What you say?
Maybe I'm not understanding. Sorry, let me...
I mean, you have the vibration, you have the fiber.
We have this vibration.
Yeah, and you have the fiber.
Yeah.
Also the fiber of the vibration, the sphere minus K.
Yeah.
And also the fiber of the minor tube.
Yes.
How to relate the topology of each other? They are related?
That's a good question.
The fiber of the big one, or the fiber of the one with the sphere, is just the intersection of the big one with the sphere.
Yes.
So that's-
That is clear. I mean, the fiber of this are the intersection of the fibers of this with the sphere. That's okay. Now, how is the topology related?
Yeah.
I think it's a very good question, but let's go back to the classical case. Suppose you have a holomorphic function. Okay? Then, and suppose the function has an isolated critical point. Okay? Then this is the classical Milnor vibration. Let's see. In that case, the topology of this is the same as the topology of the tube. Okay, so that's okay. So what you're having here actually is the following. In this case, you have one fiber. In this case, you have one fiber which is equivalent to this. So that's no problem. And the fibers here are union of these fibers, parametrized by the elements in this line. For each point in this line, you have one of those fibers. Okay? Okay. So I think this is more or less what I wanted to speak about this. Now let me come to, there are many more things, we'll come to questions now at the end. Just let me close up by two philosophical questions. Two points that spring from a very simple question. So what? I mean, why do we care about all of this rubbish? Okay? I mean, there's not a very clear answer, but let me say a few words. First, if we go to the holomorphic setting, Milnor's vibration theorem has been a landmark in singularity theory. I mean, it has really contributed a lot in singularity theory. Now, when you consider real singularities, studying their geometry and topology is much harder than in the complex case, much harder. And we don't know so much. I think all of this helps to throw some light into the topology of real analytic singularities. I think this is a way of looking at real singularities that throws light in a way and helps their understanding. So I think that's one point, which is, I think, is interesting. Now, and conversely, as I said before, when Milnor and Hirzebruch and Briscoe and others started working on this point of view, they were not really interested in singularities, but they were using singularities to get insights into the topology of manifolds, different aspects of the topology and geometry of manifolds. And that has continued to be so for many, many years. I mean, many people working on, you have the cyber-Witten invariance, you have the Donaldson invariance, you have all these beautiful invariants. And now you want to see what they say in particular cases. You want to be able to understand them better. And for that, you need to have a factory of examples where you can put your hands on. And links of complex singularities having a natural source of such examples for decades in all different ways. And so whenever you have a singularity, you have the link, and then you can test all your invariants in there. Beautiful. But now there are many cases where that do not come from complex singularities. Okay? So for example, open book decompositions play an important role in contact geometry nowadays. Very important role. And the Milnor open books play a very important role in contact geometry. What if you consider now, for example, singularities of the form C1 to the P plus C2 to the Q, C1, C2 with a bar, okay? And then you put a C3 to the R. That's an example. Okay? So now it's not holomorphic. If you remove this, you're in the holomorphic setting. And you have a Milnor open book. Now, if you put the bar, it turns out you can show that you still have a Milnor open book. And that's something that Idea Aguilar has been studying for several years. And for example, she was able to show that the corresponding Milnor open books that you get to these singularities in general cannot be defined by holomorphic singularities. So these are new open books. So that's interesting. That's one example of why I think this can be interesting to study even for different applications to different subjects. Another example. Take F from Cn plus 1 into C, holomorphic with an isolated critical point. So we know that the link, we have the vanishing set, is a hypersurface, real complex dimension n. You take the link, and it is a 2n minus 1 closed, smooth, beautiful manifold. And a lot is known, as I said before. Now, of course, just by construction, all of these have to be, a fortiori, odd dimensional, because a complex manifold always has even real dimension. And when you intersect with the sphere, you always have odd real dimension. Now, what if you want to do something for even dimensional manifolds? This doesn't help. But you can do something very simple. Look at the real part of F. You have F holomorphic, like this, and now from here you project to R0, taking the real part. Very simple, you have a beautiful function. So for every holomorphic function, you have this is canonically defined. Easy exercise. If this has isolated critical point, this now it goes into R, has isolated critical point. And now you can consider, let me call KR, the link of this. Now this is a manifold of real dimension 2n. This is a compact, closed, oriented manifold of real dimension 2n. And this, by all the theory we know and so on, this has an associated Milnor vibration and an open book, and so on. Okay? For example, you can produce in this way compact surfaces of all genera embedded in the 3 sphere. And, well, there are many, many more kind of applications you can try to do. And I stop here. About your question. Very good.
I think another question about the definition of the deregulative. If you change the metric, I mean, not consider open book structure on the sphere, but if you change another metric, in this case, if you still have open book structure, can you say something that is all the deregulativity does not depend on the metric?
I think the topological information you get doesn't change if you change the metric. Okay? But now, coming back to the question you made before. Suppose you have this regularity and you have a minimal vibration on this sphere. You ask, did you get a vibration on a tube? The problem is this. If you have a vibration on this sphere and you have this deregularity, you have the vector field that allows you to push everything inside. The problem is that if you don't have, for example, AF condition, I don't say we cannot, I say I cannot control what's happening when you come to the tube near the boundary. Maybe it can be controlled. I haven't been able to do it. I haven't worked too much on that, and the little I've worked, I haven't been able to do it. Sorry, can you repeat?
How general is the link of reality signal? Can you compare some fields with the complex?
The real to the complex? In some cases, in general, I cannot say almost anything. For example, in these particular cases, that is very easy to answer. The link of this singularity is the double of the Milnor fiber of the complex singularity. In other words, if you take the Milnor fiber with boundary, that's a real manifold of real dimension 2n with boundary. Now you take another copy, you reverse the orientation, you glue them along the boundary, and what you get is the link of this one. Now, if you don't, it depends somehow what you want. But in a way, if you only look at real singularities, in very general, I think essentially every manifold arises like that. There's a classical paper by Selman Akbulut, Henry King, and the title is "Every Knot is Algebraic." Okay, now it depends on which properties you want, then it's more restrictive. Okay, so thank you.